evening, everyone. It is with real excitement and pleasure that I'm here able tonight to welcome Andy Parr to talk to you about dark matter and wonderful things about astronomy and astrophysics. There is a brilliant world out there. I know Andy will bring this absolutely alive for you. So on behalf of ISSP and all the schools that are involved, can't wait, and over to you, Andy.
Hi, hello everyone. Welcome to this evening's talk. And I'm going to spare you very much of an introduction about me, other than that I'm super interested in astronomy. I've studied for a master's in studying BE stars many years ago, teach astronomy as well as physics at St. Peter's. And so, yeah, I've got a real interest in tonight's subject matter, which is dark matter. So without further ado, there's a lot to cover. I'm going to try and blast through it, and then you can ask questions at the end. So here we go. Starting off with this sort of fairly zany picture, we're thinking about what's really out there in the universe this evening. So unicorn fans will like this idea. To start us off, just because we can't see something doesn't mean it isn't real. And it turns out to be an important motto for scientists who are working on the problem of dark matter in the universe, which is the topic of our talk this evening. During the talk, I'll be mentioning a few astronomy heroes and hopefully painting a picture of some of the personalities as well as the science involved in the discovery and evolution of our understanding what we currently call dark matter. I also want to take make things relevant to you by bringing in some of local references. So pay close attention. There might be some people and places that you recognize. Okay, let's start with dark matter. And when I became interested in dark matter, then the guy to really think about was Fritz Zwicky. He was working on the idea of dark matter in the 1930s. But then I did some research and found out that even before then, in the 1800s, Lord Kelvin was working on the idea of dark matter. He looked at the movement of stars in our Milky Way galaxy. And yes, they do move relative to one another. And this can be seen if you watch them carefully for a very long time. And this is an example of the kind of image that the very early images that Lord Kelvin would have been able to get with a camera and a telescope. And so it's quite challenging to do, but he did do some studies and came up with some ideas and conclusions. So he studied the moving energy of stars. So I'm going to ask Luke to play us a little video clip here of some juggling and to give you the general idea. So hopefully that's coming through on the screen. And the idea here is that when he was looking at the stars, then the stars have a particular amount of movement energy and a particular amount of potential energy. And he noticed something that he became worried about. So the jugglers are here because they're showing you a good example of objects which are changing their gravitational potential energy when they're up high to kinetic energy when they're down low. And anyway, to Lord Kelvin's surprise, there appeared to be an imbalance in the amounts of energy. In fact, there seemed to be, to him, too much kinetic energy. So imagine a weird scenario where the juggling balls, when you throw them up, they end up falling down faster than they go up. And this just isn't allowed in the universe and in physics. So not least because it will make the jugglers' lives really, really difficult. So yeah, if we could stop the video there and move along, please, Luke. So yeah, we're back when Lord Kelvin was around and studying the skies. Then he would have seen an image perhaps like this quite often, because when the skies are really clear, you can see the Milky Way stretching out in front of you. This is a picture that's taken from near to Helmsley, so not far from here. Kelvin was puzzled by the imbalance in the energies that he observed, and he tried to have an educated guess as to what this might be. And he said that it was because of extra gravity due to some what he called dark stars. And there must have been quite a lot of them, in fact. And he estimated that it would be about 1 billion dark stars out there in space. So Kelvin was probably the first person to say there might be some unseen matter in space. This is a picture of Henri Poincaré, a famous mathematician, and he got interested in Lord Kelvin's work. He himself was an interesting character. He spent precisely 4 hours per day studying mathematics. Then in the evenings, he read through academic papers. And he said he was impressed by Kelvin's ideas and mentioned for the first time the phrase dark matter. He said it was matière obscure. Forgive my French pronunciation, but it's the first person to say dark matter. However, Poincaré was not too impressed by the idea of dark matter, and he didn't think it really existed. So anyway, we're thinking about what's really out there in the space and what the universe is made of. So let's have a quick tour around here. So here we know that there are meteors and moons and planets, and we're thinking about things which are made of matter stuff, things which are made out of protons and neutrons and electrons. We look further out, we see our nearest star, Proxima Centauri. Alpha Crux is a bright star in the southern hemisphere. We see nebulas, dust and gas and dust in space. We keep touring our way around the universe, and we see bigger and bigger groups of stars as we look further out. We see clusters, and then we start to see things, if we look even further, which are swirly in some instances, which are galaxies, so cities of billions of stars. And we keep looking further and further, and we see some a few different more interesting objects we'll mention later on. So along here we can see that there are some quasars mentioned, which are much further away than some of the galaxies we were looking at further back in this image. So scientists always want to be able to quantify how much is around and what there is in space. So in order to quantify things, they want to measure how much material there is in space. And so scientists want to measure everything they can see. And in the 20th century, that meant in our own galaxy. And there are a few scientists who had the same idea actually how to do this. So what they thought was, first of all, I wonder if you might be able to just hazard a guess as to the percentage of all the mass in our solar system which is contained in the sun. And if you have a quick guess, you might want to type it into the chat box if you like, and we can have a look what your ideas were later on. So have a think, write down a number, see what you think the percentage of the matter in the whole solar system is contained within the sun. Okay. Well, I have to tell you that by far the largest proportion of all the matter in the solar system is the sun, and we're considering the sun and the planets and all the asteroids and all the objects in the Oort cloud and anything that's out there at all. 99.8% of everything is the sun. So all we need to do, and if we assume that all the other stars are like this, all the matter in all of the different star systems is mostly in the star themselves, all we need to do to work out how much matter there is in a large group of stars like a galaxy is count the number of stars and then multiply that value by the average mass of a star. And there we go, we've managed to weigh a galaxy. So yeah, 99.8% of the matter in every star system is inside the star itself. Actually, what astronomers do to count the stars is just to measure the amount of light received from a galaxy. And then to calculate how much mass there is producing this light, they end up with a value. And by this method, we can then estimate the number of stars in a galaxy. So if we go to our neighboring galaxy, the Andromeda galaxy, we estimate there are about 150 billion stars in that galaxy based on how bright it appears to be and knowing about how far away this galaxy is. There's a picture here of Edwin Hubble, who's an American astronomer in the 1900s. And with some other astronomers, he made some discoveries that made the universe seem an awful lot bigger than people had previously thought. Before Hubble, it had been assumed that the whole universe was just the Milky Way, where all the stars and all the patches of cloudy patches that we could see were just sort of clouds in space. But Hubble figured out, using a telescope that could see, and hopefully you can see in the central image here, there's some detail to the galaxy that he was observing there, and that detail he decided quite rightly were stars. So these swirly patches, these nebulas in space, were in fact whole other galaxies, just like the Milky Way, containing hundreds of billions of stars probably. So thanks to Edwin Hubble, we got a picture about a better picture about how big the universe is. Let's make a Hubble had shown that there are other galaxies that exist, and that individual stars that Hubble was able to identify in these great big islands of billions of stars were famously studied in New York. And this is a plaque which is in memory of John Goodricke, who lived in the Mansion House. And despite the disabilities that he had, he was a great astronomer, and he studied Cepheid variable stars. And he actually paved the way to further work on these kinds of stars and the discoveries that Edwin Hubble made. And so, yeah, early work in this field there was quite a lot of speculation, and lots of estimates were used to try and figure out how big the galaxies were, how many stars, and how far away they were. But gradually over time, astronomers have gotten better and better at measuring distances and sizes in space. And we can thank John Goodricke for some of his early work right here in York. So, dark matter. We'll now go properly and talk about Fritz Zwicky for a second. In the 1930s, he was a very charismatic and outspoken scientist. And at one time, he was equally well known for his very sort of clever insults, as he was for any research that he did. But one thing he did really well was to study the motion of clusters of galaxies and show that there was a huge discrepancy in the amount of visible matter that he measured compared to the total mass of the galaxies when considering how much gravity they have. He did this by observing the motion of individual galaxies, and in particular looking at their rotation speeds. So how on earth was he able to work out the rotation speed of galaxies? It was possible by using a very, very clever technique, which is used in lots of other areas of physics, and it's called the Doppler effect. And it's you will be familiar with this if I play a quick slide here. So the Doppler effect is, let's just have a quick listen. So I hope that you're hearing the F1 car zooming along there. So the idea with the Doppler effect is that the car itself, if you're in the car, is producing a single pitch of sound. And what we do is we imagine, if we're in the middle of the screen, as the car comes towards us, the pitch increases. And so we hear a higher pitch. As it's moving away, we hear a lower pitch. This happens because of our perspective from the object that's producing sound. There's a sort of graphic animation here. I wonder if it's working very well for you. But basically, the pitch changes because the wavelength gets stretched out behind the object and squeezed in front. And so this happens with sound, and we notice it with an ambulance that runs past you, or a vehicle that's zooming past. But also the same thing happens with light, because light is a wave. So the Doppler effect with light works something like this. Wavelength or frequency produces particular colors. So long wavelengths are red, short wavelengths are violet, end of the spectrum. So if an object like a yellow star is moving towards the observer here, then the light becomes blue shifted, right? The wavelengths get shorter and we get the blue shift. If the object is moving away, a yellow star moves away, then the star appears to be red. The light waves are stretched out and it becomes red shifted. So redshift is a really powerful tool, and it's used in astronomy a lot. Edwin Hubble used it when he measured galaxies. He actually measured how fast they're moving compared to us to try and figure out things about the motion of galaxies relative to us. And he called this the redshift. So he measured the redshift and the speed, and was able to make an estimate of the age of the universe. which is one of the greatest discoveries of all time. But in astronomy, we don't have time to talk about that this evening. So we're going to move on and keep down the path of dark matter. So astronomers, they've just gotten started with Zwicky looking at rotation of galaxies, and they used the redshift to measure motion of stars in galaxies to try and get an estimate of the rotation speed. And I'll try and explain that a little bit more in a second. However, there was the advent of the Second World War in the late 1930s. So research in astronomy really sort of ground to a halt a little bit there. And however, there were developments in technology that were useful, but astronomy itself, it understandably had a difficult time after the advent of the Second World War. So we're going to whiz forwards actually quite a way to another character in our story here, who's Vera Rubin. So really in the 1960s, in this field of astronomy, things started to pick up. And this is a great picture, I think, of one of the real heroes of the story of dark matter, as I mentioned, Vera Rubin. She's working here to install a new instrument on a telescope in America. And she picked up on a slightly dormant and less fashionable area of astronomy to work on. But she was very clever and capable and could have worked on anything, I think probably that she really wanted to apply herself to. But lots of areas were populated with many sort of stuffy old men. And she was actually looking for a niche that would be interesting and had somewhere to go. And she was quite lucky to find a real gem in the study of rotation of galaxies. The work that she did was built on the work of Jan Oort. You might have heard of a region in space called the Oort cloud around our solar system, where there are lots of icy objects out there. And a chap called Babcock as well, who'd done some work on rotation of galaxies. But it was Vera Rubin who really managed to go into much greater depth with her studies and discovered some unexpected facts about galaxies. So galaxies have a range of different shapes and sizes, and many of them have a spirally shape. And this is obvious when you see them face on. If you're looking at them edge on, then it's not quite so obvious. But they look swirly. And this one looks like it's rotating, like a bit like a whirlpool. It's actually an artist's impression. It's not a real galaxy image, but sort of gloss over that for the moment. It looks very swirly, is the point. With the center looking like it's spinning faster than the outer parts of the galaxy. Now, let's see if this works here. So we don't need the sound there. So if we look at our own solar system, it obeys that kind of idea as well, that the inner planets are whizzing around quicker than the outer planets. And we expect that kind of thing from rotating systems like this. So that's what we would expect of in space of a system where we have planets orbiting a star or stars orbiting the center of a galaxy. So if we look at Andromeda, as Vera Rubin did, then the Andromeda galaxy, which is our neighboring spiral galaxy, it doesn't seem to be the case. And by measuring the redshift of the stars which are approaching us on one side of the galaxy and those which are receding from us on the other side of the galaxy, Vera was able to measure the rotation speed and found out that the central disk, yes, it's sort of spinning like a whirlpool, but the rest of the galaxy moves more like a solid disk. And actually the disk and the galaxy is moving and spinning too fast. So you might notice from the graph here also that the outer region, we're looking at a place where there aren't any stars, but still able to measure rotation speed of the galaxy. And this is because she was using radio technology, which had been developed in the war, but was now being used in astronomy to measure the rotation of the galaxy in outer regions which don't have any stars, but there's still an awful lot of gas out there to be measured. And so yeah, these measurements were done by Vera Rubin, and the galaxy is spinning too fast. So could we please, Luke, play the slow-mo video for a second here? And
So as you can see from this,
yeah, we don't.
2,500 frames a second isn't nearly fast
Well, I'm just
enough
sort
to
of
see what
imagining
happened
what
there.
you can see here with this video, but essentially, when the
See it warping. Look at
DVD
that.
spins
Whoa.
really quickly,
It's moving so much.
then the slow-mo guys have caught
Look
it
at the shape of it.
at the
It's
point at
moving, like
which
the whole thing.
the rotation is too
Oh
fast,
man,
and so the
it's just shattered
forces
into
that
tiny
hold the
little
disc
bits.
together
It's just like
um,
physics don't know what
can't
to do, and the CG's just like,
can't
no,
respond
crap.
to
I'm out. I'm
the
done.
effect of the
Oh,
thing spinning really quickly,
that's
and the
amazing.
whole
See that again.
I've seen that at
disc
lower
just
speeds.
flies
I've
apart.
never seen it so clear.
They've connected it.
What frame
They've
rate was
got a
that?
DVD connected to a Dyson Hoover
28,000 frames a second.
motor, and they're sending up
Yeah,
to
you've got
ridiculously high revolution speeds, and then with a
All right,
super high
Daniel.
speed
Full
camera,
speed.
you
Full
can
speed
see
ahead.
that the thing
Warp drive
flies
on.
apart if it's spinning too fast. So
Okay.
thanks, Luke. I think that's probably enough of that video there. Get the idea. So Andromeda Galaxy is
All right, Daniel.
spinning too fast,
Full speed ahead.
and so bits of Andromeda Galaxy should be flying off into space, but they're not. And in fact, not only does Andromeda Galaxy do this, but all of these other galaxies that Vera was studying here also are spinning too fast. For the amount of, so they're all spinning too fast for the amount of gravity we think is there due to visible matter. So remember, we were counting stars, using that to work out how much mass is in the galaxy, and then trying to figure out something about their rotation. The rotation is way too fast for the amount of visible matter that is present in the galaxy. So there needs to be an awful lot of extra gravitational force holding the galaxies together. So it's gravity that holds everything in orbit around the sun, and it's gravity that holds all the stars in orbit around the center of a galaxy. And basically, based on the idea of the number of stars that you can see, there's not enough gravity from the stars, so something else is responsible for this. So yeah, it was the use of the Doppler shift in studying the rotation of galaxies, which established that the galaxies are spinning too fast. And unfortunately for Vera, in the 1960s, a lot of the credit for her work was really taken by sort of more senior male supervisors, and it wasn't until much later on in her career that she was given the full credit for all of the work that she rightly deserved. But Vera Rubin, a real trailblazer in astronomy, and a big hero for lots of people who are interested in astronomy. So well done, Vera. And we understand now that there's something missing in these galaxies, and we need to try and explain it. Let's move on to something completely separate to rotation of galaxies now. Think about some really exotic objects. So these are quasars. This is an artist's impression of a quasar. Thankfully, there isn't one in our own galaxy to have a look at. We think that they are supermassive black holes. They are living in the center of distant galaxies, and they are having an absolute feeding frenzy on material and stars which are in the galaxy, falling into the supermassive black hole and causing lots of high energy radiation to shoot out of them. They're called quasars, quasi-stellar objects, because to an unsuspecting astronomer, it was, well, it might be like looking at a very bright star, but then it turns out if you try and figure out how far away they are actually objects in a very, very distant galaxy, and they're not stars at all. We now understand that they are black holes that are feeding off matter that's around them. But they're incredibly bright. They shine brighter than all the stars which are in the galaxy that they're in themselves. So they really, really stand out. Anyway, so here's a picture of a quasar. And it looks, as I said, like a star, but actually it's a very super energetic object in the center of a distant galaxy. So astronomers spotted this quasar, and then, wouldn't you know it, they spotted another quasar here. And, well, that was just perhaps a little bit too much of a coincidence. But then astronomers started to spot this, that another patch of sky. They looked and saw a quasar. When they looked really closely, there are actually 5 quasars, identical all together in the same patch of sky, which is just way too much of a coincidence. And astronomers kept looking, and they kept finding more and more of these objects. So the 6 images here, all of them quasars. All the quasars in the image, each image, are identical, and a very, very strange scenario. Why is this happening, that we have these identical quasars all together? Well, yeah. By the way, these are Hubble Space Telescope images, and we'll have a quick look at Hubble in a second. But it turns out there's an explanation to this collection of images, and the explanation was made 100 years ago by one of the greatest scientists of all time, and so it was Albert Einstein. And he said, well, okay, he said, look at me, probably when he was on the bike, but also he said that matter curves space-time, and he said that light travels in straight lines, but in curved space-time. So what on earth does that mean, and how does it explain the quasar thing? So first of all, space-time. So we have to use our imagination and stick to 2 dimensions at the moment. So imagine that you go to a large trampoline and you sit in the middle of a trampoline. You're acting like a massive object, and the surface of the trampoline is like space-time. And then if you were to roll, if someone could come along and roll a tennis ball around you, they could probably get it to go around in a circular path. So you're acting like a star, bending space-time, and the tennis ball rolling around is acting like it's acting like a planet orbiting around the star. Okay, so then we have to take a leap forward and say, okay, that applies to 2 dimensions with a trampoline. It actually applies to 3 dimensions when you're thinking about space. So space-time is this fabric that can be bent by objects which have mass. The more mass an object, the more it bends space-time. And light also responds to space-time, as Einstein said, and light travels, or it tries to travel in straight lines, but if the space-time fabric is curved, then it moves along curved paths. So although light has no mass, it moves on these curved paths. So that's what's happening with the quasars. There's one quasar that's very far away, but its light has been bent by the curvature of space-time and producing these multiple images on the Earth. It's like a lens. And the images arriving on the Earth, they form this pretty pattern. But the thing that's causing that is a huge amount of matter between us, the observer, and the quasar. And that matter, though, is not visible, so it is dark matter. Yes, Hubble Space Telescope took those images of the quasars, and so here's a picture of Hubble just to for completeness. Brilliant telescope, likely to be trumped by the James Webb Telescope, which is out there in space now, getting ready to do its thing. But it's been a brilliant tool for astronomers for many years. So we have to give a nod to the Hubble Space Telescope for giving those brilliant images. Here's 1 or 2 other brilliant images. Hubble Space Telescope of a distant galaxy, but the one in the middle, there are lots of distant galaxies here, but the one in the middle, can you see it's got something of a ring around it? And astronomers spotted this, and once they spotted it, then they started to look to see if there were any more, and so they found another one. So we've got this sort of bluish smear around the object there, and then another one here. So these images, these effects, are called Einstein rings. Now, I suppose now that you can guess what's causing the Einstein rings, and hopefully you're thinking it's the dark matter, and you're right. So there's dark matter in between us and the distant galaxy, bending the light into a ring shape. It's acting like a lens, and it turns out that this is really good for doing calculations, and astronomers can figure out how much matter is in between us and the distant galaxy to cause this ring, and there's an awful lot. So we're finding out that there's a great deal of dark matter out there in the universe. So dark matter, we see other evidence of it. This is a famous image, which is the bullet cluster. Now, in a second, I'll ask Luke to play as a quick video clip. But this image here, this is all we've got of the bullet cluster. But astronomers have used some modeling to figure out what has caused this particular shape image. So what we can see is some pink stuff in the image, and that's hydrogen gas that's glowing pink because it's been colliding with other molecules of hydrogen. It's been energized, and the gas is around some clusters of galaxies. All right, so we've got some. Remember, galaxies are hundreds of billions of stars. We've got some clusters of many galaxies, and the dark matter, which we can't see in this image, but if I run through the simulation, you maybe get a picture. Is we think that the dark matter is kind of pulling two clumps of galaxies through one another and causing the gas to illuminate and for this particular shape to form. So if I ask Luke to see if you can now play the bullet cluster video. Hopefully you are seeing the images of the galaxies that swirl around, and the two galaxies come together, or two clusters come together, and the gas gets sort of left behind, but the dark matter passes through. So the idea here is that the dark matter has a gravitational effect in causing these clusters to come together. But when the clusters meet and collide, the matter collides with the other matter. So the gas collides with the gas, and we see it, it's illuminated. But the dark matter doesn't collide with itself, and it doesn't collide with the matter. So we think that dark matter is collisionless. It won't hit anything. So hopefully we've stopped the video, and we can see now that we've got a graphic on the screen here which shows a galaxy, and around the galaxy we understand from measurements that galaxies have a halo around them of dark matter. Now, if the dark matter is made of particles that don't collide with anything else, it'll sort of be bimbling around in a great big sort of cloud, a swirling cloud of material. How much is there? We think that in our neighborhood, and I said we'd mention our neighborhood of the galaxy, we think there are between 10,000 and 100,000 dark matter particles passing through every centimeter squared of, I don't know, your body every second. So between 10,000 and 100,000 dark matter particles whizzing through your thumbnail every second. And we don't feel any of them because they don't collide with anything. They are collisionless, but we can measure their effects due to gravity, as I mentioned before. And so that's when we add that up over the whole of our galaxy, it means that within our galaxy, the Milky Way, 20% of the matter that produces gravity in our galaxy is visible. So it's made of stars. Remember, 99.8% of everything in our solar system is in the sun. So 20% of the matter is in the star, and 80%, so the rest of it is dark matter, which is fairly mind-blowing, I think. So there is an embarrassing fact here, because there's 80% of our galaxy that we don't know anything about, only that it produces gravity. We don't know what it's made of. What does dark matter do? Luke, if you just play the final video clip, I think the galaxy formation. It's a really quick video clip, and what you will see is that it's a simulation made just up the road at Durham University at the Centre for Computational Cosmology, and it shows that normal matter clumps together around the dark matter. So we understand that dark matter is required for the formation of clumps of galaxies we think that dark matter is required for the formation of galaxies, and so the very presence of stars is down to the assistance of the gravity that's produced by dark matter. This picture here, hopefully you can see, is a graphic, but it's a real map, if you like, of part of our own universe, our sort of local regions of our own universe, and it looks very similar to the simulation that Durham University created. If they run their simulations without dark matter, they don't get clumps of galaxies forming for incredibly long periods of time. So it seems like dark matter is responsible for really the rate at which clumps of galaxies formed, and our very presence here, having this talk tonight, I think is down to the presence of dark matter in the universe. So, what is dark matter? What is it possibly made of? There are a few candidates that people discuss. Machos, I mentioned in the blurb before, if you read the blurb for the talk, massive astrophysical compact halo objects. So cold, dark planets or stars or comets, bits of ice. Anyway, potentially those things that Lord Kelvin thought of, the dark stars. So if dark matter is made of machos, then these are matter. And the evidence we saw about dark matter with the bullet cluster was that dark matter is collisionless. So we know what stars are like and made of, and they're made of matter, and so they would collide with one another. So and similarly with planets and other stuff. So we don't think the dark matter is are these machos at all, due to the evidence of collisions. That is one of the main points here. So could it be WIMPs, which are subatomic particles? So what do we mean by subatomic? Things which are smaller than an atom, things which you think are smaller than the bits that make up the nucleus of an atom, in fact. So perhaps smaller than the protons and the neutrons in the nucleus, but we don't quite know. They have mass if they are WIMPs. So WIMPs are weakly interacting massive particles. They have mass. They don't feel, they only feel the force of gravity and another special force that you might not know about yet, which is the weak nuclear force. And that's it. They don't notice other things that have charge. They don't feel the strong nuclear force, but so they're referred to as WIMPs. So this picture here, you might know this little village here, which is on the North Yorkshire coast, and it's Staithes. Now, just up over the hill there at Staithes, there's the entrance to a potash mine. And so I just like looking at the picture of Staithes there, but let's move along. So if you go down from the entrance to the potash mine there by just over a kilometre, and then go out under the sea by a few kilometres, and this potash mine is humongous. Down there, Sheffield University have got a dark matter observatory, which means they've got, well, the reason it's down in the potash mine is there's not very much background radiation down there, and they're looking for and trying to detect WIMPs. And they've got these tanks containing liquid xenon gas, looking for little flashes of light. But these experiments have been going on for many years, not only in Staithes, but around the world, different observatories. But no dark matter particles have been detected by these methods. So WIMPs, they are potentially the particles that form dark matter, but for decades, astronomers, scientists and physicists have been looking for WIMPs and haven't detected any. So what else could there be? Well, one of the candidates here, there are various different candidates. One of the candidates that was thought of and dreamt up for another to solve another problem in physics in the 1970s were axions, and they're different to WIMPs because they have much smaller mass, and there are theories that the axions might produce a flash of might decay and produce a photon of light, which would be quite good because we're fairly good at detecting light. But the trouble with the Axion in detecting it is we don't know what color of light to look for, and there are just infinite colors. We don't know what the mass is. We don't know how much energy it has, and so we don't know what color of light to look for. So it's another example, but again, we don't quite know what we're looking for here. So yeah, there are a selection of other examples here. Primordial black holes. It could have been that black holes from the very early universe are still whizzing around, but there are various different zany examples. I'm not quite sure what the fuzzy dark matter one is, but I like the picture there. Gravitinos, the idea that we can get some sort of gravity particle. Feebly interactive massive particle. I think these are just jokes. No, they are genuine examples of things which might be dark matter particles. Simply don't know. There's lots of different examples here. They've got fun names, which makes them interesting. You know, it might be an interesting thing to say. Yes, my area of study is fuzzy dark matter and gravitinos, which might be fun to say at parties. But yeah, we really don't know what dark matter is made of. We've got a map of what the dark matter around the Earth would look like. If you could see dark matter, which we can't, we think it would look like a stretched out sort of hairy elliptical shape. The reason it's stretched out in an ellipse is because of the gravity of the sun. But yeah, we don't know what it's made of, and we can only say what its effect is on gravity in galaxies. We can only say what its effect is on the bending of light from distant galaxies and quasars, but we really don't know what it's made of, and that's a big problem in astronomy that needs to be resolved, and that's not even half of the problems that we have in astronomy if you want to look at things like that, because if we look at how much energy there is in the universe, it turns out that you can convert matter into energy and energy into matter by another one of Einstein's ideas, E equals mc squared. So if you add up all the energy and all the matter in the universe, 26% of everything in the universe is dark matter. Only 5% of everything in the universe, including all the matter and energy, is normal matter. So basically all the stars. And 69%, so nearly 70% of the rest of the universe is dark energy, and we simply don't have any idea what the origin of this dark energy is as well. So huge problems for astronomy, or should I say huge challenges. So I would say to you all, please keep working really hard at school and ask lots of questions, because if you ask lots of questions, then you will get a better understanding of physics, and then one day you might be able to solve the great puzzle that is the nature of dark matter. So thank you all for listening, and I think probably I whizzed through everything so quickly there. I'm going to take the opportunity to say thanks again for listening, and do please see if you can take up that challenge. But I'm going to stop there and see if anybody has managed to dream up any questions and put them into the chat box there. So yeah, let's see if I can stop the slideshow and stop sharing and see how we're going with questions here. Yeah, so do please type in a question, and I'll see if I can address your questions. I can see that some people, the first person in, I think, instantly recognized there were 99% of the matter in our solar system is the sun. Very good. Yeah. Do we have any questions coming through?
Right, folks, that was amazing. And I finally understand all those wonderful terms, which quasars, which is a word I know, but I really didn't understand before tonight. It would be fabulous if we got some really good questions in. I'm going to start, but I'd like you guys to really type some stuff in. And thank you, Olu, that's brilliant. Before Andy answers that, what do you think the next big discovery is going to be? You've had scientists making amazing discovery with really basic technology, a telescope. Now we've got amazing technology. What do you think's the next huge push to find out?
I think one of the very exciting things that's happening, if we just stick to astronomy, one of the very exciting things that's happening is that we have the James Webb Telescope, which just a week ago today, astronomers and scientists were able to get that telescope focused on a star, not a very bright star, but just in the background of that star, it was possible in the image to see some very distant galaxies which are interacting with one another. And the thing about the James Webb Telescope is that it's working in infrared, and it's going to be able to see further back, greater distance in space, and so therefore even further back in time, so closer and closer to the very beginning of our universe. So I think we're going to get some really, now who knows what's going to come out of that, but I think it's going to be really exciting information that comes out of the images that we get from the James Webb Telescope, and might tell us about actually how did the early galaxies actually form, and more information about the early universe. I think that's going to be coming. That's going to be coming through over the next starting to come through over the next year or so. So I think that's the next big story in astronomy is going to be these images. When the first images came back from the Hubble Space Telescope, they were absolutely mind blowing. So and this telescope is an absolute step change compared to Hubble. So yeah, some really exciting stuff about the very, very early universe, I think. So shall I deal with the question that's popped up here about, so we don't know the true nature of dark matter? No. We know an awful lot about what it isn't, but we really don't know what it is. So the experiments that are done, for example, in Bulby Mine, are able to establish what the mass and energy of the particles that might produce a little flash of light in there, and they've been able to exclude an awful lot of different masses and energies, and still haven't. So they've basically excluded an awful lot of things, and they're able to tell us what type of WIMPs that aren't dark matter. So we know an awful lot about what it isn't, but we still don't know what it is. Yeah. Can you quantify? So I'm just sort of skimming through for the next question. So, oops. How do I don't know how to pop these on the screen here, but there's a question which is dark matter evenly spread, and why does it attract to is dark matter evenly spread? Why does it attract normal matter into clusters rather than having the same pull on all matter? So dark matter, it's by gravity, it seems to clump together with, sorry, normal matter seems to form into clumps around where there is dark matter. So the two seem to come together, and it's the gravitational interaction that brings everything together. So it is clumpy and lumpy. And so almost every single galaxy seems to have a dark matter halo associated with it. And the maps that we have, now there's a brilliant app that you could possibly get from that Centre of Computational Cosmology at Durham. They made a map of the universe in dark matter, and you can switch off and on the visible matter and the dark matter, and they match one another fairly well. So it's clumpy, and the distribution of dark matter, but it associates itself with visible matter. However, there are one or two odd things going on out there where astronomers have spotted there are some galaxies, just a few, that don't seem to have any dark matter halo, or hardly any dark matter halo. There's a really big question as to what's happened to that dark matter. Has it been sort of stripped away from the galaxy? Was it not there in the first instance? And how did this all come about? So yeah, the answer is it's clumpy. It associates with matter, and maybe work with the James Webb Telescope can tell us a bit more about early on what was going on with the dark matter. Could dark matter be a family member of black holes? It's so there is a school of thought that dark matter is it could be small black holes which were formed in the early universe, and I think that so if dark matter were black holes, then when objects get near to black holes, then the extreme gravitational pull causes objects to fall into black holes, and when that happens, particles accelerate to ridiculous speeds, and they start to radiate huge amounts of energy. So we would see energy being emitted by black holes if it were black holes. If the black holes are really small, then we know that small black holes evaporate, and Stephen Hawking came up with the idea, Hawking radiation. So it can't be small black holes, they'd evaporate. If it was big black holes, we would see them because of radiation. So that's probably sort of 99% the chance of them being of dark matter being black holes is not. So there we go. Do you know where dark matter came from? I think is a nice question. And we have no idea. So there are two possible answers to the question, or sort of two categories. A, dark matter was formed in the Big Bang, and so and came into existence with all the other matter and energy that's in the universe. Or dark matter did not form in the Big Bang, and somehow there has always been dark matter around. If there's any way of this is a difficult, when we try and consider time before the Big Bang, it gets really a bit difficult to talk about. But perhaps dark matter didn't come into existence in the Big Bang, and somehow the Big Bang happened, and dark matter was already there. So yeah, I think it's a really good question, and nobody knows the answer. So again, it's one for youngsters out there to try and figure out what the answer is later on, because we're struggling at the moment to really know. So with quasars, so there's a question here from Chris, with quasars, black holes and dark matter, would the gravity required to form black holes be different depending on dark matter concentration? So would the gravity required to form black holes be different? So black holes, we understand, are the effect of the collapse of a massive star, and so I don't think there's such a strong connection between black holes and dark matter concentration, sort of black holes in themselves. However, I do think that dark matter, well, we know that dark matter is associated with higher densities of matter. So there's lots of dark matter. It has resulted in collecting a lot of visible matter, like gas that and the stars are made of. So there's lots of dark matter around, then it causes lots of stars to form. And if we get lots of big stars forming, then eventually they collapse into black holes. So then there is a connection. I don't think there's a direct connection between dark matter to be made between dark matter and black holes themselves. I could be wrong, but that's my best answer to that question. If we knew what dark matter was, would be the next step. The next step would be that somebody gets a Nobel Prize for physics for a problem that's been around, that we've known about for an awful, for 100 years. So that's going to be a big Nobel Prize. And then what, I don't know. Probably once we have an understanding of something, we start to understand the nature of it, then human beings want to start taking control of things once they know the nature of things. So maybe we could do some clever trick where we can sort of make use of dark matter. I don't know if we know what its nature is, but who knows? First step, Nobel Prize.
That is a brilliant way to end. There are some fabulous questions in there, Andy. There's some really good ones coming up. And that shows how brilliant that lecture was. Those questions, these are from years 7 and 8 children. And the level of the questions shows such an engagement. Just if you are really engaged in this and you're lit up by astronomy, and you're in year 8 or year 7 or year 8, at year 9, you'll get an opportunity, if you apply for it, there's some limited places to do astronomy GCSE with ISSP and really understand this stuff. Andy, thank you loads. And all the videos did work. I know you couldn't see them, but they all worked beautifully and seamlessly, and they showed exactly what you were saying, and it was really, really helpful. So thank you loads. If someone has a burning question and really wants to find out, can they send it to me and I can send it on to you?
Absolutely, yeah, can do. Yeah, there were some trivial questions there, and I was sort of picking and choosing a little bit of the one. I'm afraid some such good questions there would be quite tricky for me to give a good answer to. So yeah, thanks for all the good questions there. I don't know what the answers are, and I'd have a go, but it wouldn't be a great answer. So I'm afraid I was picking and choosing there a little bit, but they are brilliant questions. So well done, everyone.
These are really, 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 really groundbreaking, amazing questions that haven't been answered yet, because otherwise we'd have answers. Just on behalf of ISSP and on my behalf as well, that was amazing. Thank you so much. It will be up online so you can see this beautiful. If you've got friends you wish to show this to, siblings, whatever, please go ahead. There will be a link. And thank you very much indeed. Thank you, Andy. Good night.
No problem. Good night, everyone.